There we go. All right. This unit is called Kinetics, and it is all about the study of reaction rates. And by rates, we mean speed, right? So, reaction rates, and something we call mechanisms. Mechanisms we'll get into in the later half of the unit. So first off, a chemical reaction rate is determined by monitoring the change in concentration of either the reactants or the products as a function of time, right? So time is important here in this unit. That being said, the rate of the reaction is usually expressed in units of moles per liter time. So rate units, moles per liter per unit time. Now, this unit time is variable. This can be in seconds or minutes or hours, etc. Right? It kind of depends on the actual reaction, and that component is likely to change. So you must always pay attention to what unit of time is being measured, because that's the unit that needs to go in the rate law. Okay? So, notice that moles per liter, well, that's molarity, right? So in other words, it's also measured as a change in molarity or the change in time, right? Okay. So let's take this first example here. Here we have a reaction. Okay, this looks like chlorobutane is reacting with water. Right, this guy chlorobutane. Now that you know that there's a chlorine group attached to one of the carbons, and we are going to get butanol and HCl. So, with reactions, this deals with a lots of measuring. So, initially, we are starting with a concentration of chlorobutane here at 0.1 molar. And the concentration is checked in what looks like to be intervals of 50 seconds. All right, so from 0 seconds to 50 seconds, the concentration went from 0.1 to 0.0905. And then from 50 seconds to 100 seconds, it decreased further, and it decreased further, and so on. So we have all of this data. So what we're going to do, what we're doing here in this example is we're taking what's called the average rate. And the average rate is simply when you take the change in concentration, as in the difference, divided by the time interval that it occurred over. So in this particular average rate right here was taken by taking the difference of these concentrations and dividing it by 50 seconds, right? And so it turns out that the average rate for the first interval was 1.9 10 to the negative 4. And the units are moles per liter seconds, because again, seconds is the time unit used. We can calculate the average rate for every single one of these intervals. Okay, so literally just subtract this from this, divide by 50. Subtract this from this, divide by 50. Subtract this from this, divide by 50. And so we have these rates. So, first of all, what do you notice about these rates as time passes? It's decreasing. It's decreasing. So one of the very first things you should note is that your average rate decreases as the reaction proceeds. And this should make sense because as the reaction happens, there's less and less reactant left. And reactions occur based on the number of reactants there to collide. If you have a fewer number of molecules, you have fewer things that can collide. Thus, you have fewer reactions that can take place. Okay? So, as the reaction goes forward, fewer collisions between reactant molecules because the concentration is decreasing. Okay. So, let's say we plotted the concentration of the reactant over time. So, taking the same data, we started with 0.1 molar as our reactant concentration. And then every 50-second interval, the concentration of the reactant is plotted. And of course, because this is the reactant, the concentration should go down. You're using up reactants. This reaction is taking place over a longer and longer time. There's less and less reactant. The fact that it decreases should make sense. All right? So the thing is, the rate at which it changes. This is not a straight line plot, right? The difference in concentration is reduced with each interval. And as such, then, you can't expect the slope of the line to be the same here as it is here. So, a couple takeaways. First, you know how to find the average rate. If I said find the average rate of reaction from this point to this point, you would be able to do that because you would do just this, right? Any interval I give you, you'd be able to find the average rate. But you might need to find what's called the instantaneous rate. And the instantaneous rate is found by taking the slope of the tangent line at any point. All right? So on this curve, if I give you a defined point, right, like here, all right, said, all right, what's this, or actually here, this one's already chosen. If I said find the slope at this point right here, you would first draw a line tangent to the curve, right? And that line that is tangent to the curve, you would then take the slope of. So you would define kind of like an interval that you're using, right? And you would take the change in the concentration over the change in time for the line that is tangent to that point. And that is the instantaneous rate. And what you should come away with then, after doing this several times, is that slope of the tangent line decreases in magnitude. Okay? So, the slope of the tangent line decreases as the reaction progresses. Again, because you have less and less reactant remaining. You guys okay with that so far? Okay. All right. So, the other thing that we should mention is the stoichiometry of this reaction rate. Notice that in this equation here, C4H9Cl is your reactant. Also, water is a reactant. Okay. If we're defining the change here, the rate, as the change in the concentration of the reactant over time, and if you know this rate, stoichiometrically, you also know the rate at which the product is forming, because the coefficient here of C4H9Cl is 1. The coefficient here of the butanol is 1, right? So the rate of the decrease is equal but opposite to the rate of the increase of the product. And that's what we're describing right here. You just use a mole ratio. In this case, the mole ratio is 1 to 1, but you might have reactions where the mole ratio is something other than that, 1 to 2 or 1 to 3. So you would apply that mole ratio to solve for what the rate is of something else in the reaction. Okay, so just kind of another crude example. Let's say we have a reaction A plus 2B forms C plus D. Okay, and so let's say the rate of disappearance of A is 0.35 molar per second. And so what is the rate for B? Well, you would just take the 0.35 moles of A per liter second, and you just apply stoichiometry for every, there's 2 moles of B being used for every 1 mole of A being consumed, right? So the rate would be 0.70 moles of B per second. That's all, just stoichiometry, okay? And if it's a reactant or product, then technically the reactants rates are negative and the product rates are positive because the products are being formed. All right, I don't know if I mentioned that earlier. So negative rates for reactants because they're disappearing. Positive rates for products. So this should be negative and so should have this one. Question, Ron?
So, but if the question asks, like, what is the rate of disappearance of A, you don't really need to put a sign, correct?
If they say disappearance, then the implication is that it is decreasing, so no, a negative sign is not needed, right? Yeah, so that's, just if they give you a word that implies direction, then yeah, that's not needed. Okay. So let's talk about the differential rate laws. And so differential rate laws are laws that will relate both the concentration and the rate. So the first thing we need, or here, we'll just go over the generals first. So this is the general formula. The general form for a rate law looks like this. Rate is equal to some constant multiplied by the reactant that is raised to some order. We use the variable m as the order of the first reactant. Okay, so what we need to do is we need to carry out some experiments, and ultimately we need to figure out what these variables are so that we can use the rate law for calculation. So, a couple things to note. The rate constant is only indicative of successful collisions, and we'll talk more in depth about what a successful collision is later, but just suffice to say that every time molecules collide, it doesn't necessarily mean a reaction happens. Right? You don't make every single shot you take when you play basketball, right? So we're only focusing on the successful ones, okay? The order is indicative of the number of collisions that occur, and the higher the order, the greater number of potential collisions that take place. If there are 2 reactants, then your generic rate law expands and you add a second term. Generically, we'll just call that term B, and the order of B is the variable n, the letter n. But so to find the rate law, we would take the product of the rate constant times A raised to the order m times B raised to the order n. Now, in this method, in this differential rate law, notice that products do not appear, right? Only reactants are considered. Because we're using the method of what's called initial rates. And at the beginning of any reaction, you only have reactants. If there are no products at the start of a reaction, then you have no variable to use. You have no measured concentration of anything. So that's why we base our experimental determination of reactions on the concentration of reactants. Okay? Because that's what we have to measure. That's the only thing we can measure. Now, reaction order can only be determined by experimenting. It can't be predicted. It can only be. So when I say reaction order, we're talking about M and N. right? These can only be predicted by experimental trials. So let's go through some mock data here. Let's say I have this reaction, A plus B reacts to form some product, okay? And here's what I know. I run 5 trials, 1, 2, 3, 4, 5. In the first trial, I start with concentrations of 0.1 and 0.1 for both reactants. And my initial rate of product formation is 0.2 moles per liter second. Okay. I carry this out 5 times, and each time I vary the combination of concentrations. Well, that should be a decimal. That's weird. So, here is how I determine the reaction order. So what I do is, and I know it's written here, but I'm going to rewrite it just to show you how to practice writing this. I am going to pick 2 trials. I'm going to pick trials 1 and trial 2. Okay? And the reason why I'm doing that is because notice that in trial 1 and trial 2, the concentration of B is held constant, but the concentration of A is what is changed. Our independent variable is the concentration of the reactants, and we're manipulating that. So the rate law, so in general, the rate 2 is equal to K times the concentration of A2 times concentration of B2 divided by rate 1, which is the constant times the concentration of A1 times concentration of B1. So first, do you see how I wrote out the rate law in the format that I showed you earlier? I did it for each trial. Rate 2 is trial 2. Rate 1 is trial 1. And I take these two. What I'm doing is I'm taking a ratio of them. Taking a ratio of rate 2 over 1. And so, with substitution, here's what I get. The second rate was 0.4, and the units are moles per liter second. And 0.2 moles per liter second. K and K. By the way, the rate constant is the same for all trials. All right, so the value K here is going to drop out here in just a second. The concentration of A for trial 2 was 0.2 molar. And remember, the brackets imply molarity. The concentration for A in trial 1 was 0.1 molar. The concentration of B was 0.1 and 0.1. All right, now I spaced these out on purpose because I'm going to draw in some parentheses. And it's these parentheses that are going to be raised to the order like so. All right, so let's do some cancellations. You do cancellation after you've taken the ratio of your rate laws. You just do some cancellations. We said K would drop out because it's the same, right? Here I have 0.1 over 0.1, which is 1, and the order of 1 is going to be 0. It's going to drop out. So really what I'm left with then after cancellation is this. Just check that and make sure that makes sense to you. Look and see what's happening. 0.4 over 0.2 is 2. 0.2 over 0.1 is 2. When we solve for the order of m, m is equal to 1. This is how we determine the order m. And the simplest way to do this is to make sure that you are able to completely cancel the concentrations of the other reactants. It simplifies this a lot, because otherwise we'd have too many variables that are unknown. Okay. Now that we know what M is, we need to find out what N is. So now, let's use dark blue here. I want to pick a combination of trials where the concentration of B changes, but the concentration of A is unchanged. So here we're suggesting trials 3 and 4. Right? So you see how A is constant, but B is what's changing? That's going to allow us to solve for the order on B, which is N. So I'm going to take rate 4 is equal to K times the concentration of A. And we know what A is, so A's to the 1. So we can write the 1 in there since it is now known. And the concentration of B is 0.2. We'll take that over the rate 3 times K times the concentration of, I'm mixing my variables and numbers here. That's okay. Okay. So I set up my rate law ratio. And so what do I have? I have 2.4 over 0.6 is equal to, and K drops out, is equal, and A drops out, is equal to 2 raised to the N. So in other words, 4 is equal to 2 to the N. N is 2. So once I know what all the orders are on all of my reactants, I can write a generic rate law as rate is equal to K times A to the order of 1 times B to the order of 2. Now we're not quite done. We're like 3/4 done. Because while I know the orders, what is still unknown is K. So now I need to solve for the rate constant. So to do that, we just take the rate law that you figured out, rearrange it to solve for K, and now we pick a trial, any trial, it doesn't matter. And we plug the values in for that trial and we solve for K, because the K should be the same for any trial. It doesn't matter which one, okay? So, just for simplicity, let's just use trial 1. So K is equal to, the rate for trial 1 was 0.2 moles per liter second. And the molarity of A was 0.1 moles per liter. The molarity for B was 0.1 moles per liter. Now this B is raised to the second power. The order is 2. All right, so 0.2 over 1, or 0.2 over 0.1 is 2, and then 2 divided by 0.01 is going to be 200, so the value is going to be 200, but we have to resolve the units. So if we look carefully, mole per liter second over mole per liter and mole per liter and mole per liter, because you see the second unit was squared, so we have to count for it being squared. So we cancel the mole per liter, and what you're left with is 1 over seconds over moles squared liters squared, which of course when you have fractional units, it's really 1 over seconds times liters squared over mole squared multiplied by the reciprocal. And so your final unit is liters squared over moles squared seconds. Okay. Now you have a working rate law because you have the orders and you have the rate constant. Right? And so this is something you'll need to go through whenever you are given experimental data. This is called the differential rate method, or the method of initial rates. So, we're going to do an example for this later on. Okay, this method, in general, here's what the orders mean. If something is first order, meaning the exponent is 1, if you double the concentration, the rate doubles. If something is second order, if you double that concentration, the rate should increase fourfold, or 2 raised to the second. If something is third order, doubling it increases it 2 raised to the third, or in other words, 8 times. So the individual orders of M and N, whatever you do to that reactant, if you double it, if you triple it, that explains, that predicts what's going to happen to the rate. And then there's what we call overall order, which is just the sum of all the exponents. Meaning, if we go back here and I said, what's the overall order? You would add up the exponents and you say the overall order is third, because the order of 1 plus the order of 2 is third order overall. All right. So here is where we try to do one on our own, right? Let's determine the rate law experimentally using these trials. And you need to find the order on A, you need to find the order on B, you need to find what K is. And then we'll check and see how you did. All right, so take a few minutes. Follow the example we just did. You want to take a ratio of the rate laws for whichever trials you choose.